Good day to you. Good afternoon, good evening, good morning, whenever you're watching this video. This is section 3.4 in your geometry course, which is all about parallel and perpendicular lines. It's kind of continuing the theme of this chapter, which is all about parallel and perpendicular lines. Our goal here, which you should make sure you have written down in your goal sheet, is to think about how I can relate, or how you can relate, parallel and perpendicular lines. And we're talking about some properties that go along with them, or how we can prove that things are parallel or perpendicular. Now, if you've ever heard of parallel parking, you definitely will once you start taking driver's ed. Parallel parking is basically trying to park your car so it's parallel to the curb. You'll notice in that picture, I thought this was a pretty awesome picture. So it looks like a picture of perpendicular parking to me. And it works nicely because it's such a short car, but I thought that was pretty funny. But anyway, here's a little intro to what we're working on. A little situation here. It's in your notes. It says Jude and Jasmine have school together, or leave school together to walk home. Then Jasmine cuts down a path from Schoolhouse Road to get to Oak Street, and Jude cuts down another path to get to Court Road. Below is a diagram of the route each follows home. What conjecture can you make about Oak Street and Court Road? Now, a couple opening questions here. One says, what is the relationship between Oak Street and Schoolhouse Road? And you can tell there she's just cutting down this path, but it's actually labeled here nicely. This is labeled right here. And this is labeled right here that those angles are congruent. And if Schoolhouse Road goes like this, and Oak Street goes like this, and if those are two alternate interior angles, that means Oak Street and Schoolhouse Road must be parallel. Same thing goes with Schoolhouse Road and Court Street. Those are also parallel. So I guess the conjecture that maybe you could make is that Oak Street is parallel also then to Court Road. And this question 2 says, how can extending the paths help to determine the relationship between Oak Street and Court Road? Well, we know that parallel lines never intersect. So if we could continue them forever and they never intersected, we could show that they are parallel. But with that, we are going to talk about a few theorems that deal, one of them deals just directly with the situation here, and some others with parallel and perpendicular lines. So we're going to start with theorem 3.8. It does not have a particular name, but it states that if two lines are parallel to the same line, kind of like we just did in that situation, both lines are parallel to that middle road. If two lines are parallel to the same line, then they're parallel to each other. So for instance, if A and B are parallel, and B and C are parallel, then, then lines A and C are also parallel. It's almost very similar to what the transitive property would be, only now we're dealing with parallel lines. All right? So that's a good one that we'll be able to use. The next one is theorem 3.9. No special name for this one either. But this one says, in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So if we have like a transversal and both of these two lines, M and N, are perpendicular to T, then they're going to be parallel to each other. So it says if line M is perpendicular to line T, and line N is perpendicular to line T, then line M is parallel to line N. And I think later on we're going to actually prove that theorem. Because remember, theorems you can prove. So we're going to prove that using some other things that we know. Our last one actually has its own name. It's called the perpendicular transversal theorem. Theorem 3.10. This one, again, if you look at the picture, it's dealing with a transversal that is perpendicular to one of the lines. It says in a plane, if a line is perpendicular to one of two parallel lines, then we can say that it's also perpendicular to the other one. So if line N is perpendicular to line L, and both L and M are parallel, then line N is also perpendicular to line M. And by the way, if you haven't caught on, the parallel sign is the two lines go parallel, and the perpendicular sign is this little upside down T that shows it's making two 90-degree angles there. So those are perpendicular. So those are the three new things for this section. I want to apply them, and then we're going to prove one or two things next. So let's first apply one or two of these theorems. All right, we've got a little map here. It says a developer is planning a new housing complex, and the map of the complex is shown at the right. Assume that all streets lie in a plane. So there's some angles even labeled here. So the angle 4 would be this angle right here. Angle 3 is this angle right here. Angle 2 is this one right here. And angle 1 is this one right here. So it says if Washington and Lincoln streets are to be parallel, so Washington and Lincoln are to be parallel, what must be true of angles 1 and 2? Well, we know this from section 2, or I think it was section 2 or 3, that if two lines are parallel, then their corresponding angles are congruent. So that means that angle 1 is congruent to angle 2. So there's one thing we would know for sure about those. I don't think we have anything else that we'd need to know about angles 1 and 2 other than they're congruent. I mean, they very well may be right angles, but we don't have anything about perpendicular lines yet. B says, which streets must be parallel if angles 3 and 4 are congruent? Justify your answer. So if we're looking at them being parallel, this angle goes with this and this angle. They're both on those lines. And then the transversal would be this American way here. So the two lines that are parallel would be those two streets. I think it would be Washington Street and Jefferson. And then American Way would be, American Way would be the transversal for those two, showing that those two alternate interior angles are congruent. Now letter C says if measure of angle 1 is 90 degrees, and your answers to parts A and B are true, to what roads is Eagle Road perpendicular? So if it's perpendicular to, well, if angle 1 is 90 degrees, then it's perpendicular to, let's say, Eagle, oh, stop it. Eagle would be perpendicular to Washington, and that's simply just because of what it says in this. It says measure of angle 1 is 90 degrees. All right, and we said that Washington and Lincoln are both parallel, so these angles 1 and 2 would have to be congruent. So that would also be perpendicular to Eagle Road. So what is going on? I'm sorry, something's going on with the computer. But anyway, we were saying, well, Eagle will also be perpendicular to Lincoln. That kind of comes from that theorem. If a line is perpendicular to one of two parallel lines, then it's also perpendicular to the other parallel line. It looks like Jefferson is also perpendicular to Eagle, but I don't think we have enough information to prove that right now. So that's what we have there, that Washington and Lincoln are both perpendicular to Eagle Road. All right, the rest of this section kind of deals with a couple of proofs. I wanted to quick prove at least one of these. The first one is the proof of Theorem 3.9. So look back at what Theorem 9 says. Theorem 3.9 says, in a plane, if two lines are perpendicular to the same line, then they're perpendicular to, or then they're parallel to each other. So what we're given here is that this is in a plane, and line R is perpendicular to line T, and line S is also perpendicular to line T. So again, that's going to be your first step. So R is perpendicular to T. S is perpendicular to T. That's given. we're trying to prove that R and S are parallel. So if we know things are perpendicular, by the definition of perpendicular, we could say that, let's just say this is angle, well, that's angle 1, oh yeah, this is angle 1. We'll say that's angle 1, and that's angle 2. So we know that angle 1 and angle 2 are both 90 degrees. Let's see. Not even that specific. We can say angle 1 and angle 2 are right angles. That's just the definition of perpendicular lines. Okay, if they're both right angles, then we know that the measure of angle 1 is equal to 90 degrees, and the measure of angle 2 is equal to 90 degrees as well. Definition of right angles for that one. Let's see, if they're both equal to 90 degrees, then I think they're equal to each other. So the measure of angle 1 is equal to the measure of angle 2. That would just be simply substitution, I would say. If that's our substitution, if those angles are equal, those angle measures are equal, we can then say, and this step I don't think you necessarily need, but angle 1 is congruent to angle 2. And that's just from the definition of congruence. You don't necessarily need that one. I'm putting it in here. And since those are congruent, then we can say that line R is parallel to line S. And that's simply, I think that was one of the theorems from last chapter. That would be the converse of corresponding angles theorem. Since those are corresponding angles, and if they're congruent, then those lines are parallel. And that's what we try to prove. So it makes us happy. Now, we could have technically skipped step 3. I think we have a theorem already that says that all right angles are congruent. And then if we wanted to skip step 5, knowing that those two angle measures are the same, that'd be the same thing. That would work for the corresponding converse of the corresponding angles theorem. But I just wanted to be as specific as I could be here to make it clear what I was trying to prove and how I was proving it. Now, there is one more theorem here. Let's see, what time are we at? 13 minutes. Let's do this one and then we'll be done. So it says in a plane, we know it's line C is perpendicular to line B. Line B is perpendicular to line D. And line D is perpendicular to line A. That's all given to us. It's also labeled here. We got all these right angles labeled. We're trying to then prove that line C and line A are perpendicular. Line C and line A are perpendicular. Well, let's actually use some of these theorems we just came up with. We just got them in this chapter. We're not proving one of them. We're trying to use them now. So why don't we look at if we know that both line C is perpendicular to line B and line D is also perpendicular to line B. They're perpendicular to the same line, so that means line C is parallel to line D. And which theorem was that? if they're perpendicular to the same lines of the parallel. That would be theorem 3.9, the one that we just proved. So that's theorem 3.9. Let's see. I'm trying to prove C is perpendicular to A. So if we know that these are parallel, so let's see. Now we have D, and D is perpendicular to B, and D is also perpendicular to A. That would mean that A and B then are parallel. That would be the same theorem. So we have C is parallel to D, and A is parallel to B. These are parallel. These are parallel. I'm trying to prove that C is perpendicular to A. It doesn't extend all the way over there. But if we can say that, let me think for a second here. I'm not sure if we had to say all that, but we could then say that, so since C is perpendicular to B, and A is also perpendicular, or hold on, see if let's look at this theorem right here. It says, in a plane, if a line, this is our last one, if a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. So if we know that both C and D are parallel, and we know that B is perpendicular to, or A and B are both parallel, and B is perpendicular to C, then A would also be perpendicular to C because of theorem 3.10. And technically I should switch this around. C is perpendicular to A. We'll just say that's reflexive right now. Oh, not reflexive, symmetric, sorry. But the main one there is step 4. Just knowing that we can use that theorem 3.10, that if we know that two lines are perpendicular, they are parallel, and then one of them is perpendicular to, or a line is perpendicular to one of them, it's going to be perpendicular to the other one. All right, so that proves what we're trying to prove, that C and A are perpendicular, those lines. If you'd like to try these error analysis ones and the closing questions on your own, that'd be great. We'll briefly go through them next time if we have time. But otherwise, have a good rest of your time. We'll see you next time.